testing. My name is Stephen Kell from the University of Kent. I'm your chair for this session. And our first speaker is August from the University of Illinois Urbana-Champaign, and he'll be talking about reflection-aware static regression test selection.
Okay, so hi everyone, my name is August. I'm presenting our work, Reflection-Aware Static Regression Test Selection. This is joint work with my colleagues Milica, Lingming, Darko, and Owolabi. We're from University of Illinois at Urbana-Champaign and University of Texas at Dallas. And also a quick plug is that Owolabi is actually going to be joining Cornell next year as new faculty there. So I'd like to start the presentation just giving some background, giving the high-level description of the standard development cycle, where the idea is that developers are hacking on the code, they're adding new features, making changes, and when they do, they commit these changes to version control, which then triggers a continuous integration server, a CI server, to go and take the new code and then proceed to build and test that code. And the result of the CI server is going to be some pass-fail status, where if things are failing, for example, if you see some test failures, this indicates that there was some bug in the change. And the developer should go look at the failure, go to debug, fix it, recommit some new changes, try to fix that. And this cycle, this loop continues until we get to the point where the build and test pass, in which case the code can be released, deployed, and the developer can move on to the next feature. So even for one feature, you can get a bit of time to go through this cycle of building, testing, and making sure that the code is working. And in particular, what we're worried about here is actually this test part on the CI server. So the practice is known as regression testing, where the idea is that we want to rerun the tests after every change to ensure those changes do not break any existing functionality. There's no bug in the change. And the problem here is that this process in particular is quite slow. And the reason it's slow is due to two factors. One is that the test suite that has to be run is very large. Just kind of throw some numbers out there that's been reported is that Facebook is saying that after every change, they're running on the order of 10,000 tests. Then we compound that with the second factor, which is that changes are actually happening very frequently. Just another number we find is that Google is saying that they're making more than 20 code changes by developers every minute. And while I'm kind of getting numbers from different companies, they kind of have similar frequencies and size of tests between companies and in other companies as well. And with this factor, we're running lots of tests and always running tests because there's changes happening so frequently. We're wasting a lot of developer time waiting for tests to finish to see if there are results and they can move on, and also the machine time to actually run these tests constantly. And so companies are adopting a way to sort of and speed up this regression testing, particularly using regression test selection. So the idea of regression test selection is that while we may have a lot of tests to run to check on the code, when someone makes a change to the next version, these changes are typically rather small. And in turn, that means that not all tests, their outcomes can actually differ because of this change. So only a subset of the tests actually can have a different outcome, and means they can actually detect the bugs in the change. And so really, we only need to run these tests on the next version. And we're saving time because we're not running all the other tests whose outcomes did not differ from before. We already know what their outcomes are. And there are many ways to actually do the regression test selection. So I'm going to talk more in detail about one way, which is the static regression test selection, static RTS. So to go into more detail, we can take the code that we want to test and try to make a dependency graph out of it. And the idea is that we want to take the source code files, like the Java files the developers are modifying, and divide them into these, treat them as different files. These are the nodes in the graph. Also, we have to treat the fact that they're relying on library code as well. So there's classes in the library that either change very infrequently or never change at all. Basically, this is stuff that the developer is not writing themselves, but they still depend on, and their code still depends on. And of course, test is also code as well. So you have test classes that depend on that they have to run. The dependency edges are computed all statically, and they're based on what classes use other classes or what classes inherit from others. And so then, given this structure, we can then determine what are the tests to select when we say what class actually changed, and go backwards from the dependency edges to see, okay, in this case, we only have to run tests in T3, and we're saving time by not running the tests in the other test classes T1, T2. So this is a static way of doing test selection, and so you might imagine there's a dynamic way of doing it, which is to get these, basically works very similar, but getting dependencies from running tests on instrumented code to collect what classes tests actually depend on during runtime. In comparison to this dynamic RTS, static RTS does provide some benefits. In particular, it has very fast analysis because it's doesn't require to run tests on instrumented code, doesn't have that overhead from that. It just has to analyze the code structure. And basically, it doesn't actually have to run tests at all. So if you have tests that are run incompletely or are break in some way, you're not going to miss dependencies because of these broken test executions. On the flip side, there are some disadvantages to using static RTS. One of which is that it can over-approximate what tests to select. Basically, it's compared to dynamic RTS, it's selecting more tests than actually whose behavior can differ because of the change. So we're running more tests than necessary, and that can slow down the overall regression testing time. Unfortunately, in our own prior work, we actually evaluated this time aspect. We measured end-to-end time of a static RTS technique and found it very similar to actually the dynamic RTS techniques. But the flip side is that it can actually do the opposite, where it can actually under-approximate selected tests, which means it can be missing the select tests whose outcomes can be affected by the code changes, and therefore can miss bugs in the change because it's not running tests that can find those bugs. And this is actually the problem we want to focus on in this particular work. Specifically, what we want to ask is if the problem of reflection, this programming language feature reflection, and how does that make static RTS unsafe? It can miss the select tests that are affected by the changes. So reflection is a programming language feature that allows the code to modify its own behavior at runtime. In particular, in Java, there's these 4 reflection methods we identified in the Java standard library, which can make difficult for static RTS. One of which, for example, is class.forName. This method takes as input basically the name of the string, the string that represents the name of the class, and then it outputs the actual Java class instance for that class with that name. And the idea is that once you have the class, the code can then manipulate that class, like make instances of it, call methods on it, basically start using it, have a dependency on this class. And we have other methods in the library that do something similar, even one that takes like a byte array that defines the actual contents of the class. And the problem with these methods is that it's allowing the code to basically make references to make dependencies on classes that a static analysis cannot find by just analyzing the code structure. And so this usage of reflection of any of these reflection methods can make static RTS miss the select tests that it should select based on the changes. So kind of to illustrate an example, let's consider the dependency graph I showed from before, and let's look at some code behind this graph. So I'm going to show some bit of code for each of these nodes, and I'm going to highlight sort of the important parts of it. To start with, we have the library code. So this is something they're not modifying. It's actually in the Java standard library. That's class L. Classes A1, A2, and A3 are the classes that the developer has written they want to test. In particular, A3 is the one that actually has a change. And of course, test T1, T2, T3 test those classes. Now, the edges we can obtain by analyzing this code statically to find the relationship between classes. For example, class A1, this edge exists here because it extends L. A2 makes a new instance of L, so that's where that edge is coming from. And the tests are making either new instances of the classes A1, A2, A3, or calling methods on them. So those are those edges. And that's basically all the edges we can find at the class level from a static analysis. But the problem is that this code actually still uses reflection, particularly here. L is calling class.forName of some string S. That's actually being passed in at runtime when code calls im, passes the string A3 in. So at runtime, we actually see there's really a relationship between L that's calling class.forName that depends on A3. So we're missing this edge, and this can lead to us not selecting to run some tests, which could be affected when A3 actually has a change. So the problem is that we're missing edges in this dependency graph that are due to reflection. So what we want to propose some reflection-aware static RTS techniques that recover these edges. So we can try to do this either purely statically to figure out what the edges are missing just from some static approach, or we can actually try some hybrid static and dynamic approach. We use some dynamic analysis to figure out what are the actual reflection that's being used in the code. So I'm going to talk about these techniques more in detail in the coming slides, as long as our results of it. Though I think it's only fair at this point, I do give an upfront notice, is that at the end, our results are actually kind of negative, in the sense that in our attempt to try to make these techniques that reflection aware, we're actually slowing them down to the point that it seems almost unnecessary to run these techniques in comparison to running all tests at once without any selection, retest all. Or in the cases where it seems reasonably we're saving some time, it's potentially unsafe. It's still missing to select some tests. I'm going to talk more of details about why and sort of show those results in the end, so don't tone out now. So let's start with naive analysis, string analysis. I'm lumping these two together, and in a bit you'll see why. So naive analysis is very straightforward. The idea is that we're going to really over-approximate the use of reflection by basically saying that any class that uses one of those reflection methods, just assume they can reach into any other class. So this is, as you might expect, very imprecise. It's a very big over-approximation. So we try to make it a bit better by using a bit of string analysis. So this is kind of a strategy used in static analysis to take care of reflection in other domains beyond usage for RTS. And the idea is that since most of the methods use some name of the classes to figure out what the class actually is, we can try to track those strings to figure out where reflection, kind of guess at what the reflection actually is. Unfortunately, both of these analyses actually prove to be extremely ineffective for RTS. And I say that because they're selecting to run all tests after every change. So it's basically running all the tests every time. So that's not helping our goal to speed up testing. So naive analysis, as you might expect, is very over-approximate. And string analysis is actually becomes also as much over-approximate as naive analysis because we have to analyze the Java standard library. So I don't have time to go over the exact details about why this is a problem. Those can be found in our paper. But what this prompted us is that we need to find a way to do this analysis to figure out how do we recover reflective edges without having to analyze the Java standard library. And what that led us to think about is to do this idea we call border analysis. And the idea here is that only a few of these standard library methods actually lead to calling one of those reflection methods. So what we want is these border methods, which is a method that may lead to invoking a reflection method. And therefore, we see if any method is any part of the code is using one of these border methods, we can then approximate there and say this is using reflection. It can lead to anywhere else in the code. And now the question is, how do we determine these border methods? So one way to do that is we can try doing an over-approximation to guess at what the border methods are. Basically, take all the standard library methods and see which of them can actually reach the reflection method statically through a call graph analysis. And I say it's over-approximation because we're seeing actually over 55,000 methods are considered border methods by this way. And we call this kind of a stat border analysis that uses these border methods as static border analysis because we're determining these border methods statically. Now, we can try to look at the other extreme, which is an under-approximation, where we say that the border methods we consider are only those four reflection methods, for example, the class.forName. So you have to use one of these methods to actually say that you're using a border method and you're using reflection. The problem here is we're going to be missing indirect calls inside the Java standard library that could eventually call class.forName, for example. And we call this analysis four-method border analysis because we're using those four methods. Now, finally, we consider something kind of in between, where we decided that maybe we can use a bit of dynamic analysis to at the very least help us find what are these border methods for this specific project. Basically, on offline, we run the tests once on the instrumented code, and from this execution, figure out what are border methods from running these tests, and then reuse them for later changes. And the one thing to note is that this is still border analysis. It's still purely static, because once we found the border methods, even though we found them dynamically, we're still going to just use those border methods for each selection in the future on the different changes, and that's still going to be static, because we just give it the border methods straight up. As to how we're going to find those border methods, the idea is that we're going to run the tests. Eventually, we trace it into a find, say, class.forName. At this point, we look at the stack trace and see what's the first method that's sort of not in the standard library that's being called here. And the method it's calling is going to be the border method, because it's calling this method in the standard library, eventually called class.forName. And again, the name we call this is dynamic border analysis, because we're finding the border methods dynamically. So to illustrate how this works now in the overall scheme of the selection, basically all classes that call border methods connect to all other classes. At least that's our approximation. So we see that in the code, the method a1.m1 calls the border method l.m. So we say it can connect to any other class in the project. So when a3 changes, we don't just select T3, we also select T1, which can potentially be affected by the changes on A3, but we don't have to select T2, so we're still saving some time from test selection. So those are kind of purely static ways of doing selection, and now we consider maybe we can use a bit of dynamic analysis, some dynamic information, as we do the selection. So again, borrowing from some strategies we observed from making other static analysis techniques reflection aware from other domains, can we execute a test on instrumented code and figure out when is reflection being used, what's the actual reflective classes? So for example, in the project, we're running the tests, and we see that only when the tests run, it only actually reflects into A3 from here. So that's the only time it's calling class.forName, and it received A3. So then when the class changes here, we can go backwards on the edges, and these are all the tests that will be affected by the change. Unfortunately here, we're actually very, we're safe as in like we're running all tests. We're not missing anything, of course. We're also running everything. So it's taking too much time. We might as well just have run all tests to start with. So we wanted to make this a bit more precise. And we considered that we could do the similar thing here. We still use dynamic analysis to figure out what are the reflected classes. But we want to label them, the edges we have in the graph, based on the individual tests. Basically, when we run the tests, we note that this edge only appeared because it ran T1. So this edge only exists for the sake of determining if T1 is affected by the changes. So when we do the backwards tracking for when the change happens, we see that we only have to run T1. T2 didn't actually execute a reflective edge here. So let me now describe I'm going to describe the techniques, how we actually evaluated this. We evaluated on 24 open source projects from GitHub, and we're measuring, one is safety precision of this techniques. And I'll talk about what safety precision means in a bit, but basically we're measuring what tests are selected, are they selecting the right number of tests, and what are the dependencies of these tests, are they done correctly. We're also caring about performance of these techniques. Are they running fast enough? So are they selecting a few enough tests, and what's the end-to-end time of running these techniques? And finally, since we're dealing with dependency graphs and we're making it reflection aware by adding more reflective edges, what are the sizes of the graphs at the end? So I don't have time to talk about all these research questions. Their answers are found in the paper. We're going to talk about RQs 1 and 4. So RQ4 is the safety precision of the tests selected, and basically are we selecting too many or too few tests? And we're comparing this with respect to Ecstasy, which is a state-of-the-art dynamic test selection tool. And what we're going to measure is, first we're going to say what are tests selected by Ecstasy, so that's X. And T, let's say, is the test selected by one of our techniques. So we want to see if there are any safety violations. Basically, are we missing to select some tests that Ecstasy selected that we should? And precision violations are the opposite. Are we selecting too many tests, more tests than Ecstasy said we should select, and therefore we're too imprecise. So the basic reflection unaware version that doesn't take reflection into account already has some safety violations and some precision violations. And when we add reflection awareness to it, to one of the techniques, one is we say look at precision, and we see that it goes up as expected because we're adding more tests because of the reflection. They all kind of go pretty high, at least for the border and dynamic versions, over 50% precision versus the 26 from before. Per test actually increased just a little bit, just like 29, up to 29%. For safety, on the other hand, it's lower, so that's good. So we're handling some of the reflective cases, but it's not completely safe. It's not zeros. So why is it still unsafe? We actually have a few reasons for unsafety. Details, again, are found in our paper. I don't think I actually have time to talk about a specific reason we had, but there's a specific reason why per test analysis is actually unsafe. I don't have time to talk about that. I guess all 4 of them are now found in the paper. So let's talk about end-to-end time. So the idea is that is it worthwhile to run these RTS techniques? So basically this red line represents 100%. That's where if you just run all tests without any of this fancy test selection, how do you compare against that time? And clearly we see cases where we're not doing so good, especially for dynamic analysis. It's both taking too much time to run the tests instrumented and selecting too many tests to run. So we have cases where it's some clear outliers here. And overall, we're not doing so great compared to 100%. The retest all 100%. It's all very close there. We also consider the fact that maybe some of the analysis we do can be brought offline. So like constructing graphs, we don't have to do that before telling the developers what tests are run and what the results are. So we take those parts of the analysis offline. Things are looking better, times are closer, but at the end of the day, a lot of these analyses are still pretty high, still kind of close to 100%. The best reflection aware in terms of time is this per test one, but from before we saw that per test is actually unsafe. So overall, our results actually seem rather negative, that the techniques are either like impractical in the sense that it's running too long, it's very close to just running all tests without using selection, or in our cases where it's actually seem to save some time, it's still unsafe, so we're still missing to run some tests that we should. And this is kind of prompting us to say, wait, we need kind of help now. We need a way to develop some perhaps RTS-specific reflection analysis to basically achieve our goals that we want fast analysis to allow us to select what tests are affected quickly, while still being able to make it run the tests that should be affected by the changes. Particularly some other directions that we think might be interesting to look into is that if it really becomes kind of impossible to make it completely fast and also safe, actually nowadays we're seeing a bit of a trend, a push towards unsafe RTS, where industry is saying, okay, we actually care more about time. Let's try to save on that direction more. And some direction we go is, okay, how are these comparing? How unsafe actually are they compared to some more safe RTS techniques? How do they compare that in that direction? Or we should maybe work on improving that base reflection unaware RTS to reduce its over-approximation, and in turn that will make the reflection-aware techniques even faster. So to conclude, static RTS is rather unsafe due to reflection, and we try to make it reflection-aware through 5 reflection-aware static RTS techniques. But we found that at the end they're currently either taking too much time to run, or even still remain unsafe afterwards. So what we really want is again, it's a call for help that we should try to think about, can we make a static analysis that's reflection aware, but also good for the domain of RTS? So if you have any questions, please feel free to email me. Of course, I'd be happy to take questions now. I think before I end, I'd like to make a quick plug, is that I also work on other stuff besides RTS, including things like flaky tests, other ways of speeding up testing, mutation testing, all sorts of stuff. And the reason I'm putting that up because actually I will be on the job market coming up. So if you're interested in that other work I do, including this one, please also feel free to contact me. And that ends my presentation.
Okay, we have time for 1 or 2 quick questions. Any questions?
Is this off? No. Thanks for your talk. You mentioned reflection methods, but what about any other side effects, maybe like global variables being mutated or things like that? Would that trigger also a need to run other tests that you would not run? And did you take that into account?
So the question is, are there other factors beyond those 4 reflection methods I mentioned that could be affect? So the reason why we focused on those 4 methods in particular is we're looking for patterns of of methods that allow you to take a reference to a class that's not present in the code. So things like actually invoking methods on the class you get, or trying to access fields in it, to do that you have to already have the class instance already. So either that's going to be in the code directly or gone through one of these methods. And we want to trade those cases where the standard static RTS will not be defined references to the classes in the code already.
So to me, the basic problem here is deeper. And tell me why I don't, what I say is not correct. So to me, the problem is that you have analyses that are not sound in the presence of reflection. So if you had an analysis that is guaranteed to be sound, at least, to find you an over-approximation, for example, of the call graph, you would not have this issue. Of course, you know, you might select the whole test suite, but am I missing anything?
So the question is that right now our analysis is not sound. Like, since it's not taking reflection, it can't find the reflection if it is pure on the static code, and that's why we're missing these tests. Yes, that's part of the problem. We do want to be able to find the tests that are affected by the changes, so we make it more sound, potentially, as you said, writing all tests. But we also have to care about the performance of the selection, that we want it to be, at the very least, particularly faster than just running all tests. Otherwise, if we just run all tests, we're already going to be safe and sound. But we want to save time over that baseline. So we want it to not just be sound, but also fast enough to be worthwhile to use as we regression test.
Yeah, perhaps I missed the connection of your activity that says, if you are, you know, here is the formula that tells me I'm maximizing the tests that I'm saving times the soundness, or something like some notion of measure that you're trying to optimize here.
So yeah, as I understand the question is that here we're trying to optimize for is we're trying to be safe. We're trying to consider all the cases that can be affected by reflection. But as we try to do that, we're sacrificing time. And basically I'm saying is that that's also unacceptable. So a lot of the ways we're trying to kindle reflection is kind of through what we've seen from other domains of static analysis, trying to take care of reflection in those places, but those are not working here for our specific domain of RTS. And perhaps we can do something where we can maybe not go directly to reflection, but do take some advantage of knowledge of other parts of the test to say at least to get the final effect of what tests are actually affected by the change.
Okay, I think we should press on, but let's thank our speaker again.